Hey everybody, welcome back to number theory. Last time we proved that there are infinitely many primes and did some other proofs as well. Today we're going to be looking at a way of putting an upper bound on how big the nth prime can be. So there is, no matter what n is, if n is the 1,000,000th prime number, we want to be able to put an upper bound on that and say, you know what? The 1,000,000th prime number can't be any bigger than such and such. Now, we may not know what the 1,000,000th prime number is, but we can put a bound on how big it can be. And we can do that for any natural number n. The nth prime number can be no larger than such and such. And that's our ultimate goal today. First, we do a lemma that we're going to use in a subsequent theorem. And again, this is all directing us to being able to put a bound on how big the nth prime number can be. The finite geometric series 1 plus r squared plus r cubed and so forth is equal to this thing. So if we add up all the terms of our finite geometric series, this is what we get. Now, you remember from Cal 2 that we have a geometric series if each term of the series is equal to some constant times its predecessor. And that constant we call r, the ratio. So in this case, the second term is equal to r times the first term. The third term is equal to r times the second term. The fourth term is equal to r times the third term, and so forth. So this is a finite geometric series. There are only finitely many terms. And we are trying to prove that when we add up the terms from 1 to r to the n minus 1, we get this number. So let's go ahead and prove it. The first thing that we're going to do is we're going to put a name on this sum to make it easier to work with. So whatever it is the terms of this finite geometric series add up to, we're going to call it S. And I'm going to call this thing equation 1. I'm not sure why, other than the fact that I have a tendency to do that sort of thing at times. So we'll call this thing equation 1. Next, what we're going to do, because I actually do have a plan here, I'm going to multiply both sides of equation 1 by r. So every term on the left gets multiplied by r, and the right gets multiplied by r. There, I just multiplied both sides of equation 1 by r. And I'm going to call this thing equation 2. And I'm going to subtract equation 2 from equation 1. By the way, this is somewhat of a standard trick when using or when working with geometric series. So it might be worth our while to go over this proof a couple of times. So subtract equation 2 from equation 1. 1 plus r squared, r cubed, dot, 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 r to the n minus 1. And that equals s. There's equation 1. And equation 2. r squared, r cubed, r to the n minus 1, plus r to the n. And holy moly, all of these things wipe each other out. And I'm left with 1 minus r to the n. And that's equal to s minus rs. I can factor a capital S out of this thing. And if I factor s out of the first term, I get 1. If I factor s out of the second term, I get r. Remember what S was. S was the thing that our original geometric series added up to. The sum of 1 plus r squared dot, 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 plus r to the n minus 1. That's S. So maybe we'll be more explicit there. 1 minus r to the n over 1 minus r is equal to, oh my goodness, forgive me. 1 plus r squared plus r cubed plus dot, dot, dot plus r to the n minus 1 equals 1 minus r to the n over 1 minus r. That's what we set out to prove. Now let's look at a special case. Okay, r equals 2. Then we have 1 plus 2 plus 2 squared plus 2 cubed equals plus 2 to the n minus 1 equals 1 minus 2 to the n over 1 minus 2. Well, 1 minus 2, that's just negative 1. Now this is probably what we're really going to be using when we try to get a bound on how big the nth prime number can be. And we're going to use strong induction to do that. This may be the first time we've ever used strong induction. And let's see, are we ready to do this yet? I don't think so, but no, we're not quite ready to prove it yet. We have a lemma first. And oddly enough, the lemma that we're about to prove is in some way or other connected to our proof that we did the other day to show that there are infinitely many prime numbers. There's a connection between the proof we did the other day and the lemma that we're about to prove. So here we have the first k plus 1 prime numbers. This is the first prime number, so this would be 2. This is the second prime number, that would be 3. This is the third prime number. That would be 5, and so forth. The k plus first prime number has to be less than this product plus 1. Now, do we see something that's familiar? What about this number right here? Didn't we see this in our proof that there are infinitely many prime numbers? But we're going to do very much the same thing with this number today that we did a few days ago when we proved that there are infinitely many prime numbers. We're going to suppose that this isn't true, and we're going to see what happens. So we're going to suppose the negation of this thing, namely that the k plus first prime number is greater than this number p. Now, just to show where we are here, this number this number is capital P, the product of the first k prime numbers plus 1. Now, our claim is that if we take the first number after the kth prime, in other words, p sub k is our kth prime number. Take the number that follows that, that's composite. The number after that one is composite. The number after that one is composite. Dot, 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 up to and including the product of the first k primes, this is composite. The sum of the first k primes plus 1, which is capital P, this is composite also. So all of the numbers after the kth prime number and before the k plus first prime number have to be composite. And let's just draw a diagram of that to illustrate. Now remember how we started out. We're putting all of our primes in order. Here's the smallest one, P1. Here's the next smallest one, P2. Here's the next smallest one after that, P3. Here's the kth prime number, which is smaller than the k plus first prime number. The subscripts of these prime numbers put the prime numbers in ascending order. And we're saying, for the sake of deriving a contradiction, that the k plus first prime number is greater than this number from our infinite primes proof. Well, here's the same number down here. And here's the same number down here. This is our capital P. Now, what are all of these numbers? Well, this is the kth prime number. And this is the very next prime number, p sub k plus 1. So think about it. If p sub k is the kth prime number, and p sub k plus 1 is the k plus first prime number, then all of the natural numbers in between p sub k and p sub k plus 1, they all have to be composite. This can't be a prime number because this is the next prime number after p sub k. So all of the numbers between the kth prime number and the k plus first prime number have to be composite. This is composite, that's composite, this is composite, that's composite. All of those have to be composite. And we're going to focus on this one again. In 2 successive lectures, we run into this number. And I guess this is going to be our second observation. No, not quite. Okay, that's the second observation that we want to make. None of those prime numbers are divisors of p. And we might remember why from our proof the other day. But just as a refresher, let's visit that line of logic again. Each of these primes is a divisor of p minus 1. And p minus 1 equals P1, P2, P3, PK plus 1 Yep. Here's P. And this whole thing is P minus 1. Well, the ones just wipe each other out. So, hold on a minute. Oh, shoot. Hold on a minute, everybody. I just got a terrible message on my computer. Oh, thank goodness. Yeah, my computer was about to shut off because the battery was going low. But here's where we are. Each of these prime numbers is a divisor of P minus 1. Well, look at what P minus 1 is. It's the product of the first K prime numbers. So absolutely, each of these K prime numbers divides P minus 1. Now, what about the K plus first prime number, P sub K plus 1? Is that a divisor of P or P minus 1? No, it can't be, because by our hypothesis, our contradiction hypothesis, we assumed that the K plus first prime number was bigger than P. So the K plus first prime can't be a divisor of P minus 1. So in other words, all of the prime numbers that are less than or equal to P fail to be divisors of P minus 1. I'm sorry. All of the primes less than P are divisors of P minus 1. Now, what does this mean? So none of the first K primes can be divisors of P. And remember what happens. Suppose that some prime, P sub I, where I is somewhere between 1 and K, suppose P sub I does divide P. Yeah, if p sub I did divide p, then it would also have to divide the difference of p and p minus 1, since p sub I would be a divisor of both of these. And what does that mean? It would mean that p sub I divides p minus p minus 1. Oh, but what is this? That's just 1. So that would mean that p sub I divides 1. And since p is a positive number, that means that p sub I equals 1. But this contradicts the fact remember, 1 is neither prime nor composite. Prime numbers have to be at least as big as 2. Composite numbers have to be at least as big as 2. So if we assume that p sub I divides p, we end up with the contradiction that p sub I equals 1, and that means that p sub I is not really a prime after all. So, none of the primes that are less than p are divisors of p. And certainly, any prime larger than p can't be a divisor of p. So this means that p has no prime divisors. Now, what's the problem with this? This contradicts the fundamental theorem of arithmetic that says that every natural number greater than 1 can be written as the product of primes. So there's our contradiction. And this is what led to the contradiction. We were assuming that the k plus first prime number was greater than this famous number p. There we did it. We proved that the k plus first prime number has to be less than or equal to this magic number p, the product of the first k primes plus 1. So this theorem puts a bound on how large the k plus first prime can be. The only problem is, do we really know what this number is? Well, yeah, it's the product of the first k primes, but suppose k is 150,000. Okay, the k plus first prime is less than or equal to the product of the first 150,000 primes plus 1. Well, do we really have any idea what that is? I'm sure we don't. And so we're going to take this result, which is actually a lemma, and we're going to turn it into a result that will make sense to us. It'll put a bound strictly in terms of a number, not the product of primes, most of which we don't know. So we are going to conclude this with a theorem that will put an upper bound on the kth prime number, or the k plus first prime number. And that upper bound will be something that sort of makes sense to us numerically. So this is the nth prime number size-wise. A piece of 1 would be 2. Piece of 2, the second prime, would be 3. Yeah, let's just get some sense of this. P1 is 2, P2 is 3, P3 is 5, P4 is 7, P5 is 11, and so forth. And we're talking about the nth prime number size-wise. So P sub n is such that there are exactly n minus 1 primes less than this. So size-wise, this is the nth prime number. And I'll label my proposition. That's my proposition, capital P sub n. In other words, this thing is true for all natural numbers n. So for 1, this is my proposition evaluated at 1. I just took P sub n and I plugged in 1 every place I saw an n. Okay, P sub 1 equals 2. And I'm really hoping that this is less than or equal to 2 to the power of 2 to the 1 minus 1. Well, let's see. This is 0, so 2 to the 0 is 1. Okay. So yes, my first prime P sub 1 satisfies this relationship. P sub 1 is less than or equal to 2 to the power of 2 to the power of 1 minus 1. Okay. That works. Now, normally at this point, we'd assume that P of n is true for n equal k. But in strong induction, we have to do this. For strong induction, we're assuming that our hypothesis is true for k in all natural numbers less than k. Now I'm going to write this out again. And what is my proposition? The nth prime number is less than or equal to 2 to the power of 2 to the n minus 1. Is that it? Yes. For all natural numbers less than or equal to k, and then I need to show that my proposition is true for n equal k plus 1. So that is the k plus first prime is less than or equal to 2 to the power of 2 to the k plus 1 minus 1. Now I can tidy this up a little bit. K plus 1 minus 1 is just k. So essentially, this is what I have to show. This is what we showed in our previous lemma. Oh, this is so slick, it's incredible. This is slick. Now this first prime, by our induction hypothesis, is less than or equal to 2 to the power of 2 to the 1 minus 1, which is 0. This thing, by our induction hypothesis, is less than or equal to 2 to the power of 2, and n is 2 here, so this is 2 minus 1 is 1. And this thing, by our induction hypothesis, is less than or equal to 2 to the 2, n is 3 here, so 3 minus 1 is 2. By our induction hypothesis, this is less than or equal to 2 to the power of 2, and n is k here, so this is k minus 1. Ah, okay. So our k plus first prime, this guy, is less than or equal to the product of all of these things plus 1. Whoops, whoops, whoops. K minus 1. K minus 1 right here. This is 2 to the power of 2 to the k minus 1. So 2 to the power of 2 to the k minus 1. Okay. Now, I have 2 to a power times 2 to a power times 2 to a power. What do the exponents do? Don't they add? So I should be able to do this. 2 to the power of 2 to the 0 plus 2 to the first plus 2 to the second plus 2 to the third dot 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 plus 2 to the k minus 1 plus 1. If I only knew what to do with the sum of these exponents here. Oh my goodness. Well, maybe as I'm erasing the board, it'll come to me. I'm not going to change this much. I'm just going to change that thing, 2 to the 0. And I'm also going to write a little bit larger. I'm looking for a flash of inspiration, and I think I have it. That was something that we proved in a lemma earlier on. So we are looking good now. We are looking very good because I know what to do with these exponents. So I have the k prime, k plus first prime, less than or equal to 2 to the power of the sum of these things, which is just 2 to the k minus 1. Oh, okay. Now let's see, can I do that? Well, what happened? These two things are the same. This thing is larger than that thing. So yeah, I'm just saying this is greater than or equal to that. And as long as k is at least equal to 1, this is true. If k is 1, I have 2 to the first, which is 2, which is greater than 1. Yep. Okay, that's working. These two terms are exactly the same. We've got two of them. So I can say this is 2 times 2 to the k minus 1. And essentially that means I have 2 to the first times 2 to this power. The exponents add. We got an exponent of 1 here, although we don't see it, an exponent of 1 here. So we just add the exponents, 2 to the power of 2k. Did that come out? I hope. I think it did. Yeah, 2k minus 1 plus 1 is 2k. And I'm hoping that's what I wanted to prove. Let me see the statement of the theorem. 2 to the 2k. I haven't written this down quite right, but that's okay. The only thing that I'm going to change are the exponents. I didn't look closely enough at the statement. This thing is equal to 2 to the power of k minus 1. So I should have here 2 to the power of k minus 1. And in each case, the 1 is being subtracted from 2 to the k. So 2 to the first times 2 to this power, the exponents add, 1 adds to this, and we get 2 to the power of 2 to the k. And this is what we wanted to show. Now, how do we say that in terms of our original hypothesis? N minus 1. So this is a bound on all prime numbers. The nth prime number, no matter what it is less than or equal to this number, which is a power of 2. One more thing, and this is very important. Now, I believe a few days ago that we had homework on page 43. I think on page 43, I will see if I can get this up by the morning of April 9th at the latest. And maybe April 10th or 11th, I'll put the solutions to this up. And I need to photocopy your test ones and just email them back to you. In the meantime, keep studying. Don't worry about what we can't do. Let's just do what we can do and make the most of this time to study. By the way, it is a well-known, no, it's not a well-known fact, but it is definitely recognized as being true that Isaac Newton, the greatest mathematician and scientist of his century, the inventor of calculus, accomplished most of what he accomplished mathematically and scientifically when he was in seclusion at his family farm during a period of time when the bubonic plague was ravaging England. He left London and left the university to go back to his family farm, and almost all of the noteworthy accomplishments that are accredited to him mathematically and scientifically, he came up with while he was in seclusion at the family farm, just awaiting for the bubonic plague to subside. So he didn't worry about what he couldn't do, he just did what he could do, and he did quite a bit. And let's do what we can do, don't worry about what we can't do. Things are not going to be like this forever. We'll get through it, and maybe we'll get through it and accomplish quite a bit also. So let's do what we can do and exercise sound judgment in everything that we do, because we all want to get back together again. I want to see all of you, and I want to see all of you in good health and happy, and you want to see each other as well. So let's exercise soundness of mind so that when this is over, we'll be back in the classroom with our friends and everything will be fine. Until next time.